In this two-part talk, we're going to have a look at pointers within C++. So in this first part, we'll introduce the notion of what a pointer is and look at some of the aspects of how they can be used. And in the second part, we'll delve into the usage of them a lot more in terms of getting down to some of the nitty-gritty aspects. So as the first thing to say about pointers is that it is something that is quite closely tied into languages like C and C++. In terms of being a C or C++ programmer, you'd be quite accustomed to the use of pointers most probably. Whereas if you're coming from, for example, from a Java background, then it's less likely to be the case. There's still pointers within it, but they're not as open, as accessible, as visible to the programmer. Short of your classical null pointer exception that you quite often get in Java, accessing or trying to access a reference which has yet been to be linked to an actual object. So it's there under the surface. It's just that in languages like Java, in C and C++, we have a lot more access to them. So it's useful then to have a bit of an explore of what that access is and to understand what pointers are, how they can be used. And that'll help us our appreciation then of how other languages, in which they're hidden, roughly how they work under the surface. We'll start off with a little bit of very basic definition, but it's useful to do this because there's going to be reasonably precise use of language that they can use, even though when we're using pointer, we'll be referring to something a little bit more general and generic. Just as a remember, when we're thinking about a variable, you can see over in the box, there's a number of key pieces of information that we need to have available or associated with a variable. We have the stored value that variable holds. We have the start address in memory, where it is, and we have the number of bytes that are reserved starting at that particular address needed to hold the value that it is. And the type of the variable will determine what are valid stored values, how much memory is needed, and how we interpret that memory at that location. So for example, given the statement, you can see here int a is equal to 4. We're going to set aside 4 bytes of memory, most probably in C++ at the minute, at a specific address. And in terms of the ones and zeros across those 4 bytes from that address, we'll encode them with a pattern that will represent an integer 4. So fair enough, that's fairly straightforward. Now, if we're thinking about pointers, and we're going to get there, so it ties into the memory address as well. In C++, in C languages like that, there is a special operator that's known as the address operator, and it's an ampersand character. You can see it here, where you can go to a variable and you can ask for the address in memory where that variable is stored. So if I wanted to work out if an int a is equal to 4 and I wanted to work out, well, whereabouts in memory is that stored, I can ask to get the address in memory of it. So it's a fairly low-level operation, but it's a language feature that's supported within, for example, C++. A pointer then, so well, you can see an example. So hence over here, ampersand a is the address of variable a in memory. Now, a pointer is defined as the memory address of a variable. So when we think about a as an entity actually refers to an address in memory. So notionally, our variable a points to a location in memory. So that's the strict interpretation of what we mean by a pointer, points to a particular address. Now, a pointer value can be stored in what is known as a pointer variable. And the bit at the bottom, we're just going to call it pointer for short. So strictly speaking, you can make a distinction between a pointer value and a pointer variable. So a pointer value is in essence just an address in memory. If I give you an address, that is a valid value of a pointer, because a pointer points to a location in memory. So an address is a particular valid memory location. And a pointer variable, similar to an int a, in this case we have another variable, something we can change, but in this case it points to an address in memory. So we can change the pointer variable to point to different addresses in memory. So we're just going to call that a pointer, but strictly speaking, what we are talking about here is a variable that we can change the value of, and by changing the value of it or accessing that value, we are changing or accessing different locations within memory. That's what we're going to wrap up under the notion of a pointer. But it is useful to understand precisely in terms of pointer values, pointer variables, and just a basic pointer to a location in memory. How do we do this then? It's actually fairly straightforward to do. In terms of the box towards the top, you can see here we've got a var name of type T. So this is any type you want, and this is true of pointers. You can point to ints, to chars, to user-defined classes, whatever you want. So it's something, could be primitive, could be user-defined. Type T called var name. In line 2, there we are creating a pointer variable. So I'm saying I want to have a variable called ptr name, and it doesn't hold an int, doesn't hold a char. What it holds is an address in memory, and we're assuming it is an address in memory that identifies or points to the start of an object, a variable of type T. Now that type's important because that is the entity, the type of the variable tells us how many bytes do we need to read from that start location in memory, and how do we interpret those bytes so we correctly understand the thing we're pointing to. So we've got a pointer variable pointing to something of type T called ptr name. And in line 3, we're doing an assignment. So this is the same as saying you've got an int a is equal to 4. We're assigning the value 4 to an integer a. Doing something similar in line 3. In this case, we have ptr name. It can point to the address in memory of something of type T, and we are assigning it to the address of var name. And thankfully, var name is something of type T. So having done that assignment, then ptr name, the value held within ptr name, will be the address in memory of var name itself. So we've assigned the address through. And again, bit at the bottom really just identifies that the type tells you, given that individual address, how many bytes you need to read after that and how to interpret those bytes in terms of understanding the thing that you're pointing to. The small example here of how we might define that. So we're going to have a couple lines of code. Line 1, we're creating an int called data. It has hexadecimal value 56. And in line 2, we are creating an integer pointer called ptr data, and we're setting that, initializing that to the address in memory where data is stored. Okay, if these are both automatic variables, they'll be stored somewhere on our stack. So we're going to look at the chunk of memory we're on the right-hand side, but we're assuming that they've been located next to each other within memory. So the first one, int data, is equal to hexadecimal 56. So what happens there is we go to the start of our free store, wherever this is. We reserve 4 bytes of information because we need that for storing our 32-bit int. So notionally data as a variable then, it points to location 1000. That's where it stores its value in memory. So hexadecimal address 1000 is our memory address. Within this, we're going to store a binary representation of the integer 56. And you can see that in the address 1000 to 1003. Notionally, we're storing value 56 within those 4 bytes. After that, we're creating our integer pointer. Now, creating a variable, you need to understand its location. How big is a pointer? This is actually where the addressing space comes into things. So if you're dealing, say, with a 32-bit environment or a 64-bit environment, it can make a difference. So a 32-bit environment, your biggest pointer size, generally speaking, is 32 bits in size. If you're running in a 64-bit environment, 64 bits in size. So you can actually define smaller size pointers if you want to. But we're assuming here that when we do a pointer to an int, we'll get a 32-bit pointer. So that gives us roughly our 4 gigs memory address that we can span over. So there we're storing our pointer variable in memory location 1004 to 1007. That's our 4 bytes of reserved memory, and ptr data refers to location 1004. Now the contents of that memory, those 4 bytes, there we're storing an address, or basically the location of an address. And in this, we're storing the address, you can see it here, roughly 1000, or precisely 1000. So whenever we read the 4 bytes of memory of ptr data and we pull out the address, we can then follow that, go to that particular address, and we know there we're going to be looking up the address of our integer that we've linked it to. So it all hangs together. It's quite nice. Few little things there. I mean, in terms of, it can be useful. In fact, it is useful to be able to have the address and to point to different addresses. One of the things you're likely to want to do after pointing to something is actually to read the values that are there. So if I have a pointer to an integer, I might want to say, right, okay, I know I'm pointing to an integer, but I want to read the value that I'm pointing to. So actually read the value, for example, of that integer. Now, there's a special operator in C++ that enables us to do it. It's known as the dereferencing operator, and it uses the asterisk symbol as a way of doing that. So if I take a pointer variable and I put an asterisk in front of it, so you can see here, hence if ptr_num is a pointer to an integer, then asterisk ptr_num, that basically means get me the thing you're pointing to and get me the value of the thing you're pointing to. So if I was pointing to an integer that encoded the value 4, then asterisk ptr_num would return an integer of value 4. So basically it's a lookup of the thing you're pointing to. Given that, two examples down at the bottom, two fragments of code, they are functionally identical in terms of what they do, but they just show you an example between direct access and then indirect access through a pointer. So over on the left hand side, we've got a method called add, returns an int, takes in two ints, num1, num2. It returns num1 plus num2. It's a very simple method. Line 5, we're calling that, calling add, passing in a couple of ints. In the example on the right hand side, we've written something functionally the same, but instead of passing in integers directly and adding them together and returning them as a whole, we're going to use pointers. So you can see here that the method takes in a pointer to an integer, num1, and another pointer to an integer, num2. So we're not actually taking the integers per se, we're taking in their address in memory. At line 3 then, we are returning, and there we're using our dereferencing operator, whatever is pointed to by num1, the value of that, plus whatever is pointed to by num2, the value of that. So effectively it's the same as looking the 2 up, and we return it. Calling this method, we still might have a couple of ints, but we're not passing them in, we're passing in, as you can see in line 5, the address of where those integers are stored in memory. Now, obviously the illustration on the left, it makes sense. It's what you would implement. You wouldn't implement the one on the right. It's only shown here as by way of a simple side-by-side comparison to sort of highlight roughly how pointers work in terms of passing an address, dereferencing it, and processing the information. Why would you use pointers? Now, there is a cost to using pointers, and it was seen in the example on the previous slide. It requires effectively a double lookup. So if I have an integer variable, for example, I was passing in my num1 and my num2, I simply need to go to that address in memory and take out the integer value. So it's one lookup, so to speak. If I'm using a pointer variable, I have to go and read the value of the address I'm pointing to in that pointer variable, and then go to that address and to look up the value. So I have to look up an address, go to that address, look up the value, and then use the value. So it actually is basically 2 hops to get to where I want to get the data. So it's slower. So we're in the question of, certainly last example wasn't as elegant, and it was fundamentally slower than the first one. Why might we use pointers? There's different reasons, a couple of them sort of mentioned here. First one, the fundamental and powerful relationship between pointers and arrays. Whenever we look at this, we'll see that pointers offer us quite a sophisticated way of stepping through data and data structures in general. They may not be simple arrays, it could be lots of different structures, but we can use pointers to jump between those things quite cleanly. We also need it because in C++, if we're allocating new memory, we'll get it on the heap, and that's going to give us at least a pointer to whereabouts it is stored, though then we can basically hide that if we want to. So for a lot of algorithms, it's going to be quite a powerful feature to go down low level and to determine how we move about memory. That's going to be the main benefit as to why we will want to use them. We'll have to use them in terms of using the new keyword because we get back a pointer to the thing that we have created. A little bit here just about style or conventions in terms of how the thing is coded. At the top, you can see the standard layout that's used if you're passing in a pointer as a method parameter. So in this sense, the type, an int in this case, and the pointer symbol, the asterisk, are together. There's no space between them. Then you have a space in the name of the variable. If you're declaring a variable, it's the other way around. So in line just underneath the foo definition, we have an int. We're creating two int to be precise. PTR, a pointer to int1 and a pointer to int2. In that case, we're putting the pointer symbol, the asterisk, next to the variable name. Now, why do they do this? In fact, you don't have to do this here. It's simply by convention. It's really to do with the reason at the bottom of the screen. So you can see down at the bottom we have two perfectly valid definitions, but they're potentially confusing. So in line 1 at the bottom, we're creating we're creating first of all A and B. A is a pointer to an integer, and B is an integer. But somebody scanning this can look and see, oh, they're two integer pointers, A and B. They're not. So the asterisk really is only associated with the A. That's the pointer to integer. B is just the pointer. If you wanted to be more explicit, line 2 will make that clear where both A and B are pointers, but it looks a bit cumbersome in terms of how you've got the thing set out. So if we adhere to the coding style here, that's what people are used to, and it will look much cleaner. Piece of wisdom, takeaway on this, is that code should be written so that the meaning is apparent in the eye of the beholder. That's really important, even though the stuff that we're writing ultimately will go through some compilation process and be optimized and be executable. Other people, other than ourselves, will most probably be looking at our source code and even our future selves. And we want to write things so somebody scanning through the code, trying to understand it as quick as they can, they're going to have the correct understanding. We're not going to code things or structure things or lay out things in a way that is likely to confuse or to mislead people. That's a bad thing to do. So we want to avoid that. So general piece of wisdom, piece of advice here, anytime we're writing code, we want to make sure we're crafting it, laying it out, structuring it, giving names to the variables and so on, so that we aid other people, even ourselves later on, coming along, re-looking at that particular piece of code. Takeaways in this one here, pointers are wonderfully apparent. You'll see this in other examples, they really are. They do give us a very flexible way of manipulating data that's been stored in memory. There's lots of things we can do with them. Along with great power comes great responsibility. Care should be taken to ensure safe pointer usage. But we've yet to see illustrations where we can mess this up. But because it's a low-level feature, because we're just changing the bit of memory that we're pointing to, we have to be careful about how we do that and then how we manipulate the things that we are pointing to. We can get it badly wrong if we're not careful. And the last bit, as mentioned, code should be written so that the meaning is apparent in the eye of the beholder. And that beholder may not be you, it may be somebody else. But all of those things are good programming practices. In the next video in our pointer series, we will delve down to some of the applications and have a look at how pointers can be used in a little bit more by way of earnest or emphasis.